Swayam Prabha. Digital India. Educated India.
Hello students, welcome back to this BSc Semester 1 Honours Chemistry course, and we are discussing about chemical bonding in this particular module. This is Professor Ravin Zugade from Department of Chemistry, Rashtrasant Tukadoji Maharaj, Nagpur University, and these lectures are prepared under the academic expertise of Professor L.J. Paliwal. In this module, we are discussing about various types of bonding, including the ionic bonding, the covalent bonding, the theories of covalent bonding, metallic bonding, weak chemical forces other than the covalent, ionic and metallic bonds, and oxidation and reduction. In this particular lecture, we will be discussing about covalent type of bonding. In the previous two lectures, we discussed about ionic bonding. Now let us see what is meant by a covalent bond. Now in case of ionic bonding, we have discussed that in ionic bonding there is a transfer of electron from electropositive atom to electronegative atom, leading to formation of cation and anion, and there is an electrostatic force of attraction between the cation and anion that is the basis of formation of ionic bond. But in case of covalent bond, as the word is indicating, there is an equal sharing of electrons. So we can define covalent bond as the bond formed by equal sharing of electrons. Let us consider a few examples. For example, we know that hydrogen atom has one unpaired electron in its valence shell, which is the first shell. Now, two hydrogen atoms can share their electrons so that the valence shell configuration becomes 1s2, which is a stable noble gas configuration of helium. Another molecule, which is a O2 molecule. Now two oxygen atoms, both of them have 6 electrons in their valence shells, and they can share 2 electrons each. Thereby both of them can get 8 electrons in the valence shell, which is the second shell, and since the octet of both the atoms is completed, they get extra stability and they get a noble configuration of neon. Coming to another molecule, which is a molecule containing different atoms. For example, carbon. Carbon has 4 electrons in the valence shell. It can form 2 double bonds with oxygen atoms, each oxygen sharing 2 electrons with carbon atoms, and carbon atom sharing 2 electrons with this oxygen as well as 2 electrons with this oxygen. Now if we observe this complete configuration, we will find that oxygen is having 8 electrons now in the valence shell. Similarly, this oxygen has 8 electrons in the valence shell, and simultaneously this carbon octet is also completed. So all the 3 atoms get complete satisfaction out of the octet completion in the valence shell. So this is how the covalent type of bonding is formed, without complete transfer of electron, just sharing of electrons in between the 2 nuclei. Now we will see how the various theories of covalent bonding have developed. The first effort was made by Lewis, and he tried to explain the formation of molecules on the basis of Lewis dot structures. The atom is represented with a symbol and valence electrons are shown by dots around it. Now the dots are in pairs if they are in even number, and if there are odd dots or odd electrons, they are shown separately. When atoms combine to form molecule, the valence shell is completed, leading to stability. Consider an example that we have already seen in case of H2 molecule. The 2 hydrogen atoms can be shown like this with 1 dot each. This is what we call as Lewis dot structure. So this is dot structure of one hydrogen atom, dot structure of another hydrogen atom, leading to formation of H2 molecule with the 2 electrons present at the center of the 2 atoms. So this is how the formation of bond is explained by Lewis. Another example is of chlorine. Now both the chlorine atoms have 7 electrons in their valence shells. So one unpaired electron is there and 3 pairs of electrons are there in both the chlorine atoms. So these unpaired electrons can be shared, leading to formation of this Cl2 molecule. And in this Cl2 molecule we can see that there are 2 dots at the center. They are present in the valence shell of this chlorine atom as well as this chlorine atom. Similarly, one more example is of H2O molecule. Now this oxygen has 6 electrons in the valence shell and hydrogen is having 1 electron. So they can share their electrons, thereby oxygen is completing its octet while simultaneously hydrogen is getting 2 electrons in the valence shell. And since the valence shell of hydrogen atom is first shell, it is completely filled and it gets stability because of the noble gas helium configuration. Now once the bond is formed, the shared electron pair can be represented by a dash. So we can simultaneously show the formation of, after formation of the chlorine molecule, Cl2 molecule, the 2 dots at the center can be substituted with a dash. Similarly, this water molecule can be shown with a dash in between oxygen and hydrogen. The remaining electrons which are not involved in bonding, they are shown as it is with the help of dots. It is possible to show similar structure for ions also. For example, if we consider OCl negative ion. Now in this OCl negative ion, oxygen and chlorine, they are bonded by a single bond, and since there is one extra electron taken up by this molecule to complete their octet. So oxygen octet is complete, chlorine octet is also completed with one extra electron. So you can show it as a negative charge. So it is an anion, OCl negative ion. This can also be shown like this. Similarly, we have disulfide ion with both the sulfur atoms completing their octet, and the shared electron pair can be shown by a dash in between them and 2 negative charges because it is disulfide di-negative ion. Similarly, we can show positive ion like ammonium ion, where nitrogen is forming 4 bonds with 4 hydrogen atoms, but since there is one less electron in the structure, so now you can see that nitrogen is actually having 5 electrons in the valence shell, but there are only 4 electrons shared, with 1 electron is lost, and as a result the net charge on the molecule will be positive. This was Lewis concept, and Lewis concept was the most preliminary concept for covalent type of bonding, but the better, more appropriate and long lasting structure was given by valence bond theory. This theory was initially proposed by Hitler and London, and then further it was extended by Pauling and Slater. We will see both the aspects in details. We'll start with Hitler-London approach of valence bond theory. Every theory is based on certain postulates. So let us see what are the postulates of valence bond theory. Valence bond theory was the first quantum mechanical treatment to account for the chemical bonding. Hitler and London, they applied the quantum mechanical concept to the bond formation, and this theory was first introduced by Hitler-London in 1927 and subsequently by Pauling and Slater in 1930. Coming to the postulates, the first postulate of this is the covalent bond is formed by overlapping of atomic orbitals of 2 identical or different atoms. So the first thing which is important is the atomic orbitals should undergo overlapping for the formation of covalent bond. Secondly, only the valence shell electrons are involved in the bond formation. So whenever the bond is formed, the inner electrons or the inner shells do not undergo any change, but only the valence shell electrons undergo sharing, pairing, etc. Thirdly, the overlapping orbitals should contain unpaired electrons for sharing. Only those electrons which are unpaired can be shared. Paired electrons cannot be shared. And fourthly, the shared electrons should have opposite spins. Now, while discussing the quantum numbers, we have seen that there are 2 types of spins, one clockwise spin and anti-clockwise spin of the electron. When the electron is revolving around the nucleus, it is rotating around its own axis, and we know that electrons can be paired only if they have opposite spins. They are shown by two spin quantum numbers, plus 1 by 2 and minus 1 by 2. So the shared electrons should have opposite spins, means one should have a spin quantum number plus 1 by 2 and second should have a spin quantum number of minus 1 by 2. The overlapping orbitals should have comparable energies. If one orbital is having very high energy and second atom having orbital with very low energy, they cannot undergo overlapping, leading to formation of a stable bond. So in order to form a stable bond, the overlapping orbitals should have comparable energy, not exactly equal, but they should be comparable with each other. Coming to the energetics in the formation or bond formation, consider the formation of H2 molecule from two hydrogen atoms. Let us see this diagram on right hand side. Now in case of hydrogen atom, there is unit positively charged nucleus and one electron. Second hydrogen atom is also having positively charged nucleus and one electron. Now what are the forces which are existing in between? Within an atom, there is an attractive force between the nucleus and the electron shown by this particular arrow. Similarly, within this atom, there will be a force of attraction between this nucleus and the electron. But when these atoms are coming together or coming closer, there are four types of forces which are acting between them. First force is this nucleus will definitely attract the negatively charged electron of the second hydrogen atom. Similarly, the second electron or electron on the second hydrogen atom is attracted by the nucleus of the first hydrogen atom. So there are two attractive forces between nucleus and the electron of the other atom. Similarly, there are repulsive forces between the two nuclei. The positively charged nucleus of one hydrogen atom repels the positively charged nucleus of the other atom. Similarly, the two electrons, they repel each other. So there are four interatomic forces: attractive forces between electron and nucleus, and repulsive forces between nucleus and electron. Now when these two atoms are at infinite distance, now if you can see this diagram, this is a potential energy expressed in kilojoule per mole as a function of internuclear distance are expressed in picometers. Now consider a situation where these two atoms are far away from each other, so that this R is very high or very large value, so more than around 500 picometers. So at this distance there is no interaction between the two hydrogen atoms. But if they come closer and closer and closer, at some moment the interaction begins, and among these interactions, initially the attractive interaction is stronger as compared to the repulsive interaction, because the internuclear distance is large. As a result, there is more attraction than the repulsive forces. Hence, they start approaching each other because of the attractive forces. And we know that whenever there is attractive force, there is net release of energy, and hence the potential energy of the system goes on decreasing. So at a particular moment, suppose R, the internuclear distance is around 300 picometer. At this point, the attractive forces will be highly predominant and the atoms will come closer and closer and closer with release of energy. So potential energy of the system will go on decreasing continuously. At R is equal to 150 picometer, we can find that there is slight overlapping of the valence orbitals. Further, when the atoms come closer and closer, at a particular distance of R is equal to 74 picometer. When I am saying R, it is the internuclear distance between the two nuclei. When it becomes 74, at this particular point, the attractive forces are exactly balanced by the repulsive forces. Hence, when they try, or when if the atoms come closer, further closer, then what will happen? The repulsive forces will become predominant because of the very strong internuclear repulsion when the atoms try to come closer. Hence, from here, the energy of the system will go on continuously increasing. Now, if we observe this graph carefully, which is the most stable state, the most stable state is this point where the internuclear distance is 74 picometer and net release of potential energy is 458 kilojoule per mole. This is what is called as the bond energy, and at this moment we say that the bond is formed. Since the system is highly stable at this particular point, the atoms will not try to go in this direction or in this direction where it will have to, or whether the molecule will have to gain energy. So this is most stable state and most favored condition because of minimum energy and maximum stability. So at this particular point, we say that the bond is formed between two hydrogen atoms, leading to formation of H2 molecule, and the internuclear distance is called as bond length. This bond length is 74 picometer, and the amount of energy released is called as the bond energy, which is about 458 kilojoule per mole. This is shown with negative sign because it is the amount of energy released. Hence, we can say that at this point the bond is formed. Now, as I have already mentioned that valence bond theory is the quantum mechanical treatment for the bond formation. Now let us see how we can apply quantum mechanics to this bond formation. So consider the formation of this H2 molecule once again from two hydrogen atoms. Let us label them HA and HB. See, this is very important to understand that it is not possible to label the atoms, but this is our hypothesis, our consideration, that let us call them as HA and HB for our convenience, and let us label the two electrons on them as 1 electron and 2 electron. Respectively, they are present on HA atom and HB atom. Let psi A and psi B are the wave functions of these two electrons. When we say wave function, it is the wave function of the orbital in which the electron is present, and in this case it is the 1s orbital. So these are the wave functions of 1s orbitals of two hydrogen atoms. Now, if the two electrons remain in their parent atoms even after bond formation, then the resultant wave function of the molecule will be given by psi is equal to, now this psi is psi resultant, is equal to psi A with electron number 1 into psi B with electron number 2. Now this is a situation that can be diagrammatically shown something like this. If you have, this is HA atom, this is HB atom, this electron is still lying with A atom and this electron is still lying with second atom, even after formation of the bond, even after overlapping. Now if we put this equation or this psi value in the equation of energy given by quantum mechanics, what we get is the HH bond energy as only minus 24 kilojoule per mole and HH bond length as 90 picometer. Now you can observe that these values are far away from the actual values, which are 458 kilojoule per mole and 74 picometer. These are the actual values in case of H2 molecule. So it means that we cannot use this particular wave function where both the electrons are present with their own atoms even after formation of bond. It means that this wave function needs to be corrected considering certain more aspects. Those step-by-step corrections we will try to understand. There are three modifications which have been suggested for the wave function. The first modification is electron exchange. It is quite possible that the electron of HA atom and HB atom, initially they are present with their own nuclei, but after formation of bond, it's quite possible that there can be exchange of electron where the electron 2 can also be found near nucleus of HA and electron number 1 can also be found near the nucleus of HB. So this is what is called as the electron exchange process, and when we try to get the equation of wave function for this, the wave function can be given as psi equal to psi A1 into psi B2 plus psi A2 into psi B1. So this is the resultant wave function where the electrons are exchanged. So both of them are equally probable. Electron 1 can be found near nucleus A. electron 2 can be found near nucleus B. Similarly, electron 2 can be found near nucleus A and electron 1 can be found near nucleus B. So both of them are equally probable. This is what is called as electron exchange phenomena taking place. Second modification which was suggested regarding the screening effect. Now, when there is no bond formation and atoms are isolated, then this nucleus and this electron are facing each other and there is no screening or no shielding effect at all. But when the molecule is formed, after formation of molecule, it's quite possible that the electrons are revolving around the nuclei. As a result, it is possible that this electron is getting screened from this nucleus because of the intermediate electron which is present in between. Similarly, the same case is possible on the opposite side also. This is called as screening effect. Screening effect is the reduction in the nuclear force of attraction between the nucleus and the electron because of the presence of electrons in between the two. This is called as screening effect. So screening effect concept was applied, and third modification was suggested with ionic character introduction in the molecule. We can see that there is quite possibility that for some time or at some instance that both the electrons may be observed near the nucleus A while no electron near nucleus B, and equally probably both the electrons present near nucleus B, no electron near nucleus A. Now in this case we can see that there is a ionic character introduced in the molecule, and that ionic character will lead to a negative charge on this side and positive charge on this side, while in this case there will be negative charge on this side and positive charge on this side. But since both the probabilities or both the configurations are equally probable, the net charge on the molecule will be 0. Simultaneously, there will not be introduction of any polarity in the molecule since both the probabilities are equally probable. And when we try to write the wave function for this, the wave function can be shown as psi ionic equal to psi A12 into psi B plus psi A into psi B12. It means that this is a wave function with both the electrons in A atom, here both the electrons in B atom. B atom means it is close to the nucleus of the B atom. Hence, this psi ionic and this psi covalent, both of them will mix together to give the final wave function of the resultant molecule. Now we will see what are the effects or implications of these three modifications in terms of energy and wavelength. Consider this table. Initially what is hypothesized was this psi is equal to psi A1 into psi B2, where both the electrons are lying near their own nuclei, which lead to bond energy of only -24 kilojoule per mole with bond length of 90 picometer. Whenever we introduce the electron exchange phenomena, where the electrons are getting exchanged between the two nuclei, then the bond energy decreases substantially to -303 kilojoule per mole with a bond length of about 80 picometer. When screening effect was introduced, there is a reduction in the effective nuclear charge, and when the concept of effective nuclear charge was incorporated, it was observed that the bond energy further decreases to 365 kilojoule per mole with a bond length reducing to 76 picometer. And when the ionic character concept was introduced, we can see that this psi covalent is equal to psi A1 psi B2 plus psi A2 psi B1, and ionic wave function is given by psi A12 into psi B plus psi A into psi B12. So two electrons are present near A, two electrons are present near B, and when these two are combined together, the resultant wave function becomes psi is equal to psi covalent into lambda times psi ionic. This lambda is called as the mixing coefficient of these two probabilities. Covalent probability is stronger or higher as compared to ionic probability. But still, if we consider both of them and mix them together to give the resultant wave function, we come to a value of bond energy of the order of minus 388 kilojoule per mole with a bond length of 75 picometer, which is much closer to the observed value of bond length, even if there is a slight difference in the calculated bond energy and the observed bond energy. But still, this is a limit where we can reach by a theoretical treatment on the basis of quantum mechanics for the H2 molecule formation. All of these can be diagrammatically represented with the help of this particular picture. Now we can see that this is curve A. This curve A, then this is curve B, C, D, E and F. Now what these curves represent? This is R on this axis. R is internuclear distance versus the potential energy. The curve A is the actual graph which is observed, and this value or point Q is actually the bond formation point with the energy released is 458 kilojoule per mole, whereas the bond length is 74 picometer. Now this B curve is obtained when we use the value of psi as psi A1 into psi B2, where two electrons are present with their own nuclei. When we apply the exchange phenomena, the curve C is obtained. When we apply the screening effect condition, then curve D is obtained. When we apply the mixing of covalent and ionic wave functions, curve E is obtained. So we can see that with every successive modification, there is approach of this the calculated curve towards the experimental curve which is actually observed. Now what is this F? This F type of curve is obtained if both the electrons have parallel spins. Now if the electrons are having parallel spins, they cannot undergo pairing, and if they do not undergo pairing, there will be large repulsive forces between them because both of them are negatively charged, and because of repulsion there is a continuous increase in the energy leading to formation of no bond at all. So if the electrons are having parallel spins, there is no bond formation, but if they are having anti-parallel spins, this is actually the bond formation curve shown by this curve A. Now let us discuss the extension of Hitler and London theory by Pauling and Slater. They incorporated a new dimension of energetics as well as the directional nature of the covalent type of bonding. According to Pauling and Slater, the overlapping orbitals should have same symmetry in space so that they could overlap to considerable extent, and greater is the extent of overlap, stronger is the bond. So this is the quantitative approach towards the strength of the bond has been incorporated by Pauling and Slater. So according to this concept, more is the extent of overlap, stronger will be the bonding. SS overlap is relatively weak, while PP overlap is much stronger. This is quite obvious because the p orbitals are oriented in a particular direction, while s orbitals are symmetrical in all the three dimensions. So we can say that the extent of overlap is strongest in PP overlap, whereas it is weakest in SS type of overlapping. Covalent bond has directional character, and the direction of covalent bond is the direction in which the electron density is maximum. So if we have two atoms overlapping with each other, it is the internuclear axis about which normally the electron density is maximum, and that is the direction of the covalent bond. And since s orbitals are spherical in shape, the bonds involving these orbitals have no directional significance, but p orbital, d orbital, if they are involved in bonding, then we have two types of overlap, the axial overlap and the lateral overlap, or what we call as the equatorial type of overlapping. And hence this leads to formation of two types of bonds, sigma bond and pi bond. So whenever there is a axial type of overlapping, then sigma type of bond is formed, and if there is a lateral overlap or sidewise overlap, the pi bond is formed. We will see how these bonds are formed. According to overlap criteria as a bond for the bond strength, the strength of the bond is measured in terms of bond energy. And according to valence bond theory, just now we have seen that more is the extent of overlap, stronger is the bond. And the atomic orbitals of the bonding atoms have wave functions, suppose psi A and psi B, then the overlap integral is given by a formula S is equal to integration psi A psi B into d tau. Tau is actually a three-dimensional parameter having a value dx into dy into dz. It's a small volume parameter, infinitesimally small volume parameter, which is equal to dx into dy into dz. So this overlap integral is a measure of extent of overlap, and so as per valence bond theory, Pauling-Slater approach, we have higher is the value of S, more stronger will be the bond. And bond formation is favored only if the value of S is positive. If the value of S is 0 or negative, the bond formation will never take place. We'll see a few examples for this. So here we have S is equal to psi A into psi B into d tau, integration of this factor. Consider SS type of overlap. Now we know that S orbital is having positive wave function and another S orbital is again having positive wave function, and since psi A and psi B both of them are positive, the value of S comes out to be positive, and since S value or the overlap integral comes out to be positive, the bonding is favored. Similarly, if we have a px orbital with overlapping with the s orbital, now s orbital is having positive wave function and px orbital is also having positive wave function in this lobe. This positive and negative symbols, they do not indicate the charge. Charge on the electron is always negative, but this positive and negative signs, they indicate the sign of the wave function. So for px orbital, in one lobe it is positive wave function, in opposite lobe it is negative wave function. Now since there is a positive overlap, the value of S will come out to be positive into positive will be positive, and as a result this type of bonding will be favored. But if the approach of px orbital and s orbital is such that the negative lobe of px orbital is overlapping on the s orbital, then the product of these two comes out to be negative, and as a result this type of bonding is opposed, or bond formation will not take place like this. Another possibility is the lateral or sidewise overlap. Now if there is a overlap of p orbital, suppose this is a pz orbital with a positive wave function in this lobe and negative wave function in this lobe, overlapping laterally with another pz orbital which is again lying along z axis with positive wave function in this lobe and negative wave function in this lobe, and they are overlapping with each other, then this is positive overlap will lead to S positive. Similarly, negative into negative will again bring out S to be positive. So overall S value will come out to be positive for such type of lateral overlap. But on the contrary, if they are opposing each other, in that case you will not have a positive type of wave function like this. Suppose you have positive lobe of one orbital is overlapping with the negative lobe of other and vice versa. We will find that the S value comes out to be negative in both the cases, and such overlapping is forbidden, it will not take place. Similarly, if we have a pz orbital overlapping with a s orbital like this, is not possible, because in this particular zone if we find the product of the two will be equal to positive, but in this case it will be exactly equal negative, and hence the overall integration will come out to be 0. And since the overlap integral comes out to be 0, the bond formation is not favored at all. It means that if the value of S comes out to be positive, like in case number this 1, 2 and this 3, we can see that in all the 3 cases bond formation is favored, while in remaining 3 cases the bond formation is not favored at all, and bond will never form. We will discuss some bond parameters that need to be evaluated quantitatively whenever we are discussing various theories of bonding. The first bond parameter is the bond length. Bond length is, as the word is indicating, it is the length of the bond. It is actually the average distance between the nuclei of two bonded atoms. Now, why do we call it the average distance? Because we know that the atoms are not stationary, but they are continuously vibrating with respect to each other along the bond axis, and because of this the distance is continuously changing. The average of the minimum and maximum distance is considered as the bond length. So it is actually the internuclear distance, which is the average of all the bond lengths in a vibrating molecule. Hence, average distance has to be considered, and it is determined using spectroscopic techniques like microwave spectroscopy, IR spectroscopy, and so on. Smaller is the size of the bonded atoms, smaller will be the bond length. If the atom has larger size, definitely the overlapping orbital is always the valence shell, and since the valence shell is away from the nucleus, the internuclear distance will definitely increase. Consider this example of bond which is a FF, ClCl, BrBr and II. The bond length goes on increasing from fluorine molecule to chlorine molecule to bromine molecule to iodine molecule, because the atoms which are constituting those molecules, they are with increasing their size. Hence the bond length goes on increasing continuously. Similarly, if one of the atoms is common, the second atom is increasing in size. As a result, bond length continuously goes on increasing from HF to HCl to HBr to HI. So this is how the bond length has to be measured, and it can be determined experimentally. Second bond parameter is the bond order. Bond order is defined as the number of bonds between two atoms in a molecule. It is possible that between two molecules there are multiple bonds or one or more than one bonds. So first bond is always the sigma bond, while the subsequent bonds are the pi bonds. With increase in bond order, we know that if the bond order goes on increasing, it means that number of bonds are increasing, and if number of bonds are more, there is a more force of attraction, and as a result the atoms approach to closer extent, and hence the bond length also goes on decreasing with increase in bond order. Take an example of three molecules C2H6, C2H4 and C2H2. This C2H6 is ethane, ethylene and acetylene. Now ethane has CC single bond, ethylene has C double bond, C it's a double bond, and acetylene has CC triple bond. So bond order goes on increasing from 1 to 2 to 3, but the bond length continuously goes on decreasing from 154 picometer to 134 picometer in case of ethylene to 120 picometer in case of acetylene. So multiple bonds lead to closer approach of the atoms, leading to reduction in the bond length. Third bond parameter is the bond energy, or sometimes also called as the bond enthalpy. It is the amount of energy released when 1 mole of a particular bond is formed, or it can also be expressed in the opposite way as the amount of energy required to break 1 mole of a particular bond. Now in first case it is normally called as bond formation energy, and in second case it is called as a bond dissociation energy. For a particular bond, the bond formation energy and bond dissociation energy, they are equal in magnitude but opposite in their sign, because when we say it's a bond formation, it is the energy released, means it is considered as negative, while when the bond is to be broken, energy has to be supplied and it is considered as positive. But the equal amount of energy is released as well as required for bond formation and bond dissociation. This bond energy or bond enthalpy is inversely proportional to bond length and directly proportional to bond order. With increase in bond length, the bond energy goes on decreasing, but with increase in bond order, it goes on increasing. In polyatomic molecules of ABN type, the the average bond energy is to be considered. This is an interesting part. Even if you can see an example of say CH4 molecule, even if all the 4 bonds are CH bonds, the bond energies of all the 4 bonds are not equal. The first bond, if we want to break, we will have to supply an energy of 438.89 kilojoule per mole, while the bond dissociation energy for second bond will be 463.14. For third CH bond it is 422, while for fourth CH bond it is 338.77 kilojoule. Now this is interesting to see that even if all the 4 bonds are CH bonds, but first bond is broken from CH3H, whereas second bond is broken from CH2H, third bond is broken from CHH, and fourth is from CH. So hence the bond energy differs slightly. In such case, what we do is we consider the average of bond energy. Hence whenever we express the bond energy of CH bond in CH4 molecule, it is always the average of the 4 bond energies considered. Fourth bond parameter is the bond angle. Whenever you have multiple molecules or multiple atom molecules or multi-atomic molecules, the average internal angle between the bond pairs of electrons is considered as a bond angle. It is actually the angle of intersection of the two lines joining nuclei of the bonded atoms with the central atom. And the bond angle is governed by various factors like what is the type of hybridization. We are going to discuss hybridization in subsequent lecture, and number of valence shell electron pairs present in the central atom, the number of bond pairs and number of lone pairs, the electronegativities of the central atom and bonded atom, and presence of multiple bonds. All these factors will govern what will be the bond angle in a particular molecule. Now let us discuss an important topic of hybridization. We will discuss what is hybridization, why hybridization concept is required, and how hybridization takes place. Probably this is the most successful part of valence bond theory explained by Pauling and Slater. This was considered by Pauling and Slater a hypothetical concept but extremely important for explaining the geometries of various molecules. So let us see what is hybridization. Hybridization is actually defined as intermixing of orbitals of slightly different energies to give a new set of orbitals having all equal energies. It is purely hypothetical concept, and the new orbitals which are formed, they are called as the hybrid orbitals. Basically, it can be put in 2 words, that intermixing and recasting of the orbitals. Important to note that the number of hybrid orbitals formed is always equal to total number of atomic orbitals mixed. Secondly, the hybrid orbitals have equal energies. Hybrid orbitals have more electron density in one particular direction, and so the extent of overlap of these orbitals is more and bond formed is stronger. That we know that more is the extent of overlap, stronger is the bond. And since the electron density is pointing in a particular direction, there will be stronger overlapping with the bonding atoms. The hybrid orbitals are oriented in space in fixed direction, and so the molecules which are formed will have fixed geometry. Now what is the need for the concept of hybridization? We will try to first understand. We have seen what is hybridization. Now we will see why hybridization concept is required. There are 2 important necessities. The first necessity is to explain valency of various atoms in different molecules. Consider an example of beryllium atom. Now this beryllium is having atomic number 4 with electronic configuration 1s2, 2s2. Now if we see this atom carefully, it is not having any unpaired electron, and according to the postulates of valence bond theory, only those electrons or only those orbitals can form bond which are having unpaired electrons. And since this atom is not having any unpaired electron, it cannot form a bond. But it is observed that this beryllium can easily form various molecules like BeCl2, BeF2, where it is showing valency 2. It means that it is showing divalency, meaning that it is having two unpaired electrons. How these molecules are formed cannot be explained unless and until we consider the concept of hybridization. Second example is boron. Now boron is having atomic number 5, electronic configuration is 1s2, 2s2, 2px1. Now if we see this carefully, it is having only one unpaired electron in 2px orbital, and so it can form only one bond. But actually most of the compounds of boron, it is showing trivalency. For example, BF3. Now how BF3 molecule is formed if there is only one unpaired electron cannot be explained unless and until we consider the concept of hybridization. Third similar atom is carbon with atomic number 6. Electronic configuration is 1s2, 2s2, 2px1, 2py1. Now there are only two unpaired electrons, but in most of the compounds of carbon, carbon shows tetracovalency like in CH4. Now how CH4 can be formed if there are only two unpaired electrons and carbon is forming 4 bonds? So in order to explain the valencies of these atoms and many more atoms, in such case we have to consider the concept of hybridization. This is the first need. The second need for the concept of hybridization is to explain the geometry and the bond angles of various molecules. Let us see first the geometry component. We have BeF2 molecule, just now we have seen. Now this molecule is linear, and H2O molecule, which is again AB2 type of molecule, it is bent or V-shaped molecule or non-linear molecule. So they, even if they appear identical, BeF2 and H2O, but their geometries are entirely different. Similarly, BF3 is a trigonal planar molecule, but similar looking molecule NH3 has a trigonal pyramidal geometry. So why BF3 is planar and why NH3 is pyramidal in nature? This cannot be explained unless and until we consider the concept of hybridization. Second component of this is explaining the bond angles. Consider an example of nitrogen atom. Now nitrogen atomic number 7, electronic configuration 1s2, 2s2, 2px1, 2py1 and 2pz1. Now there are 3 unpaired electrons, and so it can form 3 bonds. Now if nitrogen forms 3 bonds with 3 hydrogen atoms using this px, py and pz orbitals, definitely NH3 molecule can be formed. But if NH3 molecule is formed like this, we know that px, py and pz orbitals are mutually perpendicular orbitals, and since they are mutually perpendicular orbitals, the expected HNH bond angle will be 90 degrees. But it is observed that the actual bond angle of NH3 molecule, the HNH bond angle in NH3 molecule is 107 degrees. So it clearly indicates that it is impossible to explain the geometry as well as bond angles of these molecules unless and until we consider a new concept, and that concept is the concept of hybridization. Now what are the steps which are involved in hybridization? In the first step, excitation of electron takes place in order to show the desired valency or desired covalency. Just now we have seen the first step is to show the desired valency. Secondly, the orbitals having slightly different energies, they undergo mixing, and equal number of new orbitals are formed with equal energy, and these equal energy orbitals are called as hybrid orbitals. Consider first type of hybridization, which is a sp hybridization. Now how will we define the sp type of hybridization? It is the hybridization which involves one s orbital and one p orbitals. They undergo mixing, and since two orbitals are undergoing mixing, two new orbitals are formed. Now both of them will have 50% s character and 50% p character, and so both of them will be named as sp hybrid orbital. So it is 50-50 combination of s and p characters. It is also called as a linear hybridization because these orbitals are arranged in a linear manner, and the angle between the orbitals is exactly 180 degrees. So this is a sp type of hybridization. Consider an example. The best example of sp type of hybridization in inorganic molecules is BeCl2. The central atom is beryllium with ground state electronic configuration 1s2, 2s2. When we apply the concept of hybridization to this, the first step is excitation of electron to higher energy level. Now the next higher energy level is 2p energy level, and in 2p we can have px, py and pz. So electron can jump to any of them. Consider it jumps to px orbital. So now the electronic configuration in the excited state will be 1s2, 2s1, 2px1. Now it is showing the desired valency 2 or desired covalency 2 because now it has to form two bonds with the two chlorine atoms. So desired valency is shown. Now from here, this s orbital and p orbital, this is 2s and 2px orbital, they undergo mixing leading to formation of two new orbitals. They are hybrid orbitals, and we know that hybrid orbitals are directional in nature. So one orbital is pointing in this particular direction with the opposite lobe having very small electron density, and second hybrid orbital is like this with large electron density in opposite direction and a very small density in this particular direction. We can put them together and we can show them like this. So one orbital having large density in this direction and small density here, and second orbital having large density in this direction and small density here. Now both these orbitals will contain unpaired electron because the contributing orbitals are already containing unpaired electrons. So two electrons, two orbitals, one electron each, because both of them are having equal energy, and we know according to Hund's law of maximum multiplicity that equal energy orbitals are filled singly, and the angle between these orbitals is 180 degrees. Now since they are singly filled, they can form bonds with chlorine atoms, and we know that the chlorine has valence electronic configuration of 2pz1. So it has got pz orbital with single electron. So this can overlap with the sp hybrid orbital of beryllium, and whenever there is a overlapping like this, the geometry of the molecule is linear, and angle, the bond angle Cl-BeCl angle will be exactly 180 degrees. This is how BeCl2 molecule is formed, and it is observed experimentally also from the spectroscopic data that it is a linear molecule with Cl-BeCl bond angle 180 degrees. It means that the hybridization concept is not only capable of explaining the desired valency, but also can explain the geometry and bond angle of this particular molecule. Consider second type of hybridization, that is a sp2 hybridization. Now as the word is indicating, sp2 hybridization will involve the mixing of one s orbital and two p orbitals. Since three orbitals are mixing, three new orbitals are formed, and they will be called as sp2 hybrid orbitals, and all the three orbitals will have 33% s character and 66% p character. It is also called as trigonal hybridization because the geometry of the molecule which is formed will be trigonal planar, and the angle between the orbitals is exactly 120 degree. Now let us consider an example of sp2 type of hybridization. The best example is BeCl3 in inorganic compounds. Now the central atom is boron with electronic configuration in the ground state as 1s2, 2s2, 2px1. Now since this is having only one unpaired electron, it has to undergo excitation to show desired tricovalency or trivalency. So there will be excitation of electron from 2s to next available higher energy orbital, which is 2py. Now in this case, the electron jumps from 2s to 2py, and hence it is having electronic configuration 1s2, 2s1, 2px1, 2py1. Now these three orbitals are having unpaired electron and they can form bonds, but first they will undergo hybridization in a way that one s orbital and px and py orbitals mixing together, and they will form three hybrid orbitals, each of them containing unpaired electron. All of them will be called as sp2 hybrid orbitals, and they are arranged in a trigonal planar fashion. Now they are forming bonds with the pz orbitals of 3 chlorine atoms, leading to formation of this BCl3 molecule. Because of the trigonal planar type of hybridization sp2, the Cl-BCl bond angle is exactly 120 degrees in this molecule. Third type of hybridization is sp3 hybridization. Now, as the word is indicating, it is the hybridization of one s orbital and 3 p orbitals. Since 4 hybrid orbitals have to be formed, or 4 hybrid orbitals will be formed, as 4 orbitals or 4 atomic orbitals are mixing. It is also called as a tetrahedral type of hybridization because the geometry of the molecule will be tetrahedral, and the angle between the 4 orbitals formed will be exactly 109.5 degree. Consider the example of CH4 molecule. Carbon ground state electronic configuration is 1s2, 2s2, 2px1, 2py1. So it is actually divalent in ground state, but it has to show tetra covalency. So it will undergo excitation of one electron from 2s to 2pz orbital, and we will have a excited state configuration 1s2, 2s1, 2px1, 2py1, 2pz1. Now the 4 orbitals or 4 atomic orbitals 2s, 2px, 2py, 2pz, they undergo mixing and they will form 4 hybrid orbitals called as sp3 hybrid orbitals, and each of them will contain unpaired electron because all the 4 contributing atomic orbitals are having unpaired electrons, and they will form bonds with the 1s orbital of 4 hydrogen atoms which are also having unpaired electrons. So there is an overlapping of sp3 hybrid orbital of carbon with 1s atomic orbital of hydrogen, leading to formation of this CH4 compound. And since there is a sp3 hybridization, the bond angle is exactly 109.5 degree, and the geometry of the molecule is perfectly tetrahedral in nature or regular tetrahedral geometry. The word tetrahedral leads to what is called as hedral. Hedral means the number of faces. When we say it's a tetrahedral, it is a geometry having 4 faces. Now if we consider this, the molecule is having 3 faces pointing upwards and 1 face at the bottom. So it has 4 faces, and so it is called as a tetrahedral type of geometry. Let us see one more example of sp3 hybridization, which is NH3 molecule. Now in case of NH3, the central atom is nitrogen with electronic configuration 1s2, 2s2, 2px1, 2py1, 2pz1. Now it is a trivalent already in nature, so we need not have to cause any excitation to show the desired covalency because it has to form only 3 bonds and already there are 3 unpaired electrons. So in this case there is no need of excitation, but yes, there is a need of hybridization. We have already seen that if these 2px, 2py, 2pz orbitals, they form bonds directly with 3 hydrogen atoms, the bond angle will be 90 degrees. But actually the bond angle is not 90 degree. That we are going to see how hybridization can explain it very well. So this 2s orbital and the 3 2p orbitals, they undergo mixing and recasting, leading to formation of 4 hybrid orbitals, and all of them will be called as sp3 hybrid orbitals. But there are 4 hybrid orbitals and 5 electrons to be accommodated among them, because already we are having 2s2, 2px1, 2py1, 2pz1. So there are 5 electrons to be accommodated in 4 orbitals. So one of the orbitals will get a lone pair of electron. So such electron pair is already present in the orbital, and so such orbital is called as the orbital containing lone pair of electrons, and it is not capable of forming a bond because there is no unpaired electron. When such atom will form bonds with 3 hydrogen atoms with 1s orbital overlapping with the sp3 hybrid orbital of nitrogen, the geometry will be trigonal pyramidal, and since there is one lone pair on nitrogen, now lone pair will occupy more space on the central atom, and as a result it will push the bonded electron pairs away from itself, and hence the bond angle reduces to 107 degree. So expected bond angle in regular tetrahedral geometry is 109.5 degree, but it reduces by 2.5 degree to 107 degree in case of NH3 molecule. One more example of sp3 hybridization is H2O molecule. Now in H2O molecule, the central atom is oxygen with electronic configuration 1s2, 2s2, 2px2, 2py1, 2pz1, and since already 2 unpaired electrons are there, there is no need of excitation. So direct hybridization of the 4 orbitals 2s, 2px, 2py and 2pz, leading to formation of 4 hybrid orbitals, but there are 6 electrons in the valence shell. So 6 electrons to be accommodated in 4 orbitals. So definitely 2 orbitals will have lone pairs, while remaining 2 are having unpaired electrons and they are capable of forming bonds. And when they form bonds with hydrogen atom with 1s orbital overlapping with sp3 hybrid orbital of oxygen, the geometry of the molecule will be bent or V-shaped, and there is further reduction in the bond angle by 2.5 degrees more to 104.5 degree in case of H2O molecule. So when we go from CH4 to NH3 to H2O, there is reduction in the bond angle consistently because of increase in the number of lone pairs. In CH4 there is no lone pair, so regular tetrahedral geometry bond angle is 109.5. Then in case of NH3 there is one lone pair, so bond angle reduces by 2.5 degrees to 107 degree approximately. And in case of H2O molecule there are 2 lone pairs, and hence there is further reduction in the bond angle to 104.5 degree. Next type of hybridization is sp3d hybridization. Now in case of sp3d hybridization, there is a mixing and recasting of 1 s orbital, 3 p orbitals and 1 d orbitals. Now the 5 hybrid orbitals are formed and each of them will be called as sp3d hybrid orbital. The angle between orbitals will be 120 degree and 90 degree. They are non-equivalent. These orbitals are arranged in a trigonal pyramidal manner. We will see with an example. Consider the formation of PCl5 molecule. Now the central atom is phosphorus with valence shell electronic configuration 3s2, 3px1, 3py1, 3pz1. Now it has to show pentacovalency in PCl5. However, it has only 3 unpaired electrons, so 1 electron has to get excited. The next available orbital will be 3dxy, and hence the excited state configuration becomes 3s1, 3px1, 3py1, 3pz1, 3dxy1. And now these 5 orbitals in the valence shell, they will undergo hybridization to form 5 hybrid orbitals which are capable of forming bonds, because all of them are having unpaired electrons, and they will form bonds with the chlorine atoms. So this is how the overlapping will take place with the pz orbitals of 5 chlorine atoms, and the geometry will be trigonal bipyramidal with the 3 bond angles 120 degree in the plane and 2 bond angles which are perpendicular to the plane will be 90 degrees. Now there is an important concept of non-equivalent hybrid orbitals. If we see that the planar orbitals are exactly at 120, 120, 120 degrees, they are equivalent, but the axial orbitals, they are not equivalent to the planar orbitals or the equatorial orbitals. So in case of trigonal bipyramidal type of geometry, we have 2 different types of orbitals or hybrid orbitals. The contribution to the equatorial orbitals is because of or from the s orbitals px and py orbital, whereas when it goes to the axial orbitals, it is the orbitals which are responsible for this are pz orbital and dz square orbital, which contribute more to the formation of these axial orbitals, and hence the concept of non-equivalent hybrid orbitals comes into picture in this case. Next type of hybridization is sp3d2 hybridization. As the word is indicating, it is mixing of 1 s orbital, 3 p and 2 d orbitals. 6 new orbitals will be formed. Each of them will be called as sp3d2 hybrid orbital. The angle between all the orbitals will be 90 degrees each, and the orbitals are arranged in an octahedral manner. We can see with the example of SF6. The valence shell electronic configuration of sulfur is 3s2, 3px2, 3py1, 3pz1. The excited state configuration, now it has to show hexacovalency, and there are only 2 unpaired electrons. So 2 electrons need to be excited from 3s and 3px to 3dxy and 3dyz. So it is double excitation. So it is a doubly excited state of sulfur, and the bond formation will take place with 6 hybrid orbitals. All of them will be called as sp3d2 hybrid orbitals, and with sp3d2 hybrid orbitals overlapping with the 2pz orbital of fluorine atoms, leading to formation of SF6 molecule with all the bond angles as 90 degree. All of them are equivalent because each of them are associated with each other by an angle of 90 degree. sp3d3 hybridization. It is the last type of hybridization which involves mixing of one s, 3p and 3d orbitals, and they will be called as sp3d3 hybrid orbitals. The angles are again non-equivalent, 72 degree and 90 degrees. 72 degree in the plane and 90 degrees perpendicular to the plane. The orbitals are arranged in a pentagonal bipyramidal fashion. The example of this type of molecule is IF7. Iodine having atomic number 53 with valence shell electronic configuration 5s2, 5px2, 5py1, 5pz1. But since it has to show heptacovalency, it has to undergo excitation leading to formation of 7 unpaired electrons in 5s1, 5px1, 5py1, 5pz1 and 5dxy1, 5dyz1 and 5dxz1. Now they will form 7 hybrid orbitals. 5 will be in a plane and 2 perpendicular to the plane. So bond angles are 90 degree and 72 degree in the plane. Again, there is a concept of non-equivalent hybrid orbitals. This is all about in this lecture. We will continue with discussion on covalent bonding in lecture number 4. Thank you very much.